We were talking about bats' wings are actually composed of a mammalian forelimb. So you can actually see, in this case, you can really only see 3 digits in a thumb. The fourth one is in there, and the inner part of the wing is actually just a mammalian arm. The wing itself is just two very thin layers of skin stretched out over this whole structure, and it's got elastin fibers to make it really to give it some elasticity, and it has this really weird set of muscles called plagiopatagiales proprii. That only took 6 months to learn how to say. That are very weird bones, very weird muscles in that they are skeletal muscles, but they don't actually articulate with any bones. They're just there to contract, to release, and control the compliance of the wing membrane, control how stretchy or how firm it is. And this is what we were saying with there is some lag. There we go. So when we're studying bat flight, there are three major areas that we like to look at. We look at the wings, which we just kind of talked about. We look at the kinematics, which is describing how is this bat moving and how does that relate back to how it accelerates, how its point properties. So how is it, how fast is it moving, how is it accelerating, which direction is it moving, all those kinds of things. And then we also have to look at aerodynamics, which is how the air is moving around, in our case, how it's moving around the wing, and how does that affect the flight. This project is all about kinematics, but in order to really understand what's going on, we do need to look a little bit at the aerodynamics, particularly an area called steady state aerodynamics. This is the field by which planes are designed. So we're making a couple of assumptions, like we're assuming that the aircraft is built with a fixed wing, not a flapping wing. We're assuming there aren't a lot of extra gusts going around. But there are two major quantities that we're going to look at. Aspect ratio, which is described as the square of the wingspan divided by the wing surface area. And technically, this is the same aspect ratio as you would see on a television, on a picture. It's just that this is wings are very rarely rectangular, so it's kind of hard to define a specific length, a specific width. Instead, we err on the side of caution and go with this formula that if you have a square wing, it's the exact same thing. We also look at wing loading, which is just the weight of the plane, the weight of the aircraft divided by the total wing surface area. And this is just saying how much does each unit of the wing, how much weight does each unit of the wing have to lift up? And so various people have tried to be very smart and applied these same things to bats. So saying, for example, this Townsend brasiliensis on top has very long, narrow wings, so it should fly very similarly to a plane that has long, narrow wings. And similarly, this Cornurinus townsendii down here has very short, broad wings, so it's going to fly much more like a plane with short, broad wings. The main important thing is we would expect long, narrow wings, like the Todderida, to fly very quickly, efficiently, but as a result have a harder time turning, whereas short, broad wings, like the Cornurinus townsendii, is going to fly much slower, experience more drag, but as a result, it can turn a lot easier. And in 1987, Norberg and Rayner, there is a citation on there somewhere, had, made this very famous figure that tries to relate a bat's aspect ratio and its wing loading to its ecological niche. So going back and saying things like Todderida brasiliensis flies very quickly because of its aspect ratio, because of its wing loading. As a result, it's going to be restricted to hunting in very wide open areas where it doesn't have to make a lot of very tight maneuvers, whereas our Cornurinus townsendii is going to be flying much slower because of its aspect ratio and wing loading, so it's going to be much better suited for hunting in vegetation than in open areas where it can be easily detected and avoided. So, the previous work on bat flight has usually been restricted to lab settings, so a wind tunnel where you just set the bat free in the wind tunnel, it flies effectively in a straight line, and you just video it, measure the kinematics, figure out how the bat is responding to various airspeeds, to maybe a turbulence that you introduce, so on and so forth. Or else they've been restricted to flight corridors, where the bat has basically a single path that it can fly. You just let the bat fly along that path, figure out how it makes that one turn or that one ascent. Furthermore, most of these previous studies have worked on simple maneuvers, so a fixed radius turn, very simple slight ascent, those kinds of things. When in reality, we know that bats are able to do much more than that. Their livelihoods are based around catching things midair, so they have to be able to change their wing conformations to account for having the tail up in their face so that they can get the prey. They have to be able to make sharp turns, sometimes around big trees, to avoid a branch in their path. And most of these studies have had very few trials. I think the most that I've ever seen was 10 trials in this study. Usually they're more like 3 or 4. These 2 papers, at least, have literally been about a single flight event. So and the reason for this is just because biomechanics work has traditionally been very labor intensive and in pushing through the data. We'll talk about that a little bit more in a second, but we wanted to start moving away from these restrictions. Instead of having a lab environment, move on to a little more natural environment and see how the bats fly when they're not restricted. Instead of requiring them to only have very simple maneuvers, let them do whatever they want. Display those much more complicated turns and try to figure out how those are accomplished. Instead of having just 3 or 4 or even 10 trials, let's try getting as many as we can. In order to actually do all this, we need a nice starting point. And so we decided to start analyzing Parneranus townsendii, Townsend's big-eared bat. Reasons being, they are very slow flyers, which makes filming them relatively simple. The shape of their wings allows them a wide variety of maneuvers that not necessarily every bat can do, things like hovering in one place. And they usually just hunt in vegetation. So if I take a bat and I put it in a relatively small flight tent that's potentially cluttered with lights and cameras, it's not going to be too disturbed by that. It's going to just be like, okay, I'm just in a forest and fly around, behave as normal. So the objectives for this thesis were, first and foremost, try to devise a repertoire of these bat flight patterns and decide, okay, what constitutes a turn versus straight flight? What makes it something ascending versus descending or level? And then go back and try to determine what is the bat doing to accomplish each of these? How is the bat behaving differently to initiate a turn rather than just fly straight? So on and so forth. So all this is great. How are we actually going to pull this off? We have actually just recently managed to publish an entire paper describing this process, and most importantly, verifying that yes, all of these methods do give us consistent, usable data. So I will be giving you the short version of this, but there are basically 3 main parts. First, we fly the bats and we video them. Second, we go in, digitize the bats, try to reconstruct their flight in 3 dimensions. And finally, we go back, analyze how is the bat changing its behavior to accomplish each maneuver. So fieldwork was done in Southwestern Research Station near Portal, Arizona, where we would go out every night, mist net for bats. If you've never seen mist nets, one, you have not lived. But I generally describe them as like very wide volleyball nets, but with very thin mesh. So as the bat is flying along in the night, depending on who you ask, either the bat can't detect the net and it just flies into it, or potentially it can detect the net, but decides it's like a spider web or something and just tries to fly forward. It gets caught in the net, and then we come along, we untangle it, and we can bring it back to our very large flight tent, where we let the bats go, let them fly, let them hunt as they desire, and we film anything cool, anything that looks like it would be good to analyze. And so you'll notice, first of all, the green light is not actually green light. This is infrared light, so the bats can't see it. We can't necessarily see it, but the cameras can. So we're filming in infrared light to not disturb the bats. And there are also 3 cameras, one roughly in each corner of the tent. They're set up so that they overlap. Their fields of view overlap right in, not right in front of, but their field of views overlap on a couple of UV lights we have hanging up to attract the moths, make the moths fly around, and thus hopefully get the bats hunting and flying mostly between those UV lights within the overlap of the cameras. And within that overlap of the cameras is where we have the best ability to go back, reconstruct the bat's flight, see everything that bat's doing. So digitizing consists of marking 16 points in each frame. Most of these points are on the wing membrane because we would like to know what is the bat doing with its wings. But we also have a couple of points marked on the body itself just to give us a better idea of where is the bat in space, where is the bat facing, all of those nice things. So we go in, we mark all 16 points in all cameras. If we can't see a point, we just don't mark it. But eventually we are able to mark as many points as we can, and we can then go back, do a bunch of fancy linear algebra, and figure out where in space are all of these points. And somewhere around here is when we can start going in and calculating, okay, this wing is extended more than this wing, all of those kinematic parameters that we'll get into in just a second. So all this sounds amazing, right? We just film, we digitize, and we dominate. Unfortunately, real life has a tendency to get in the way. So all of my numbers are cut off over there, but original goal was to analyze 99 events. There are 3 videos per flight event, 500 frames per video on average, and I need to mark 16 points per frame. We're looking at 2.5 million times I have to click on a pixel. And assuming it takes about 2 minutes for a single frame, and that is very conservative, 5,000 hours of manual processing time. Had a lot of very wonderful undergraduates help me out with this project. I've not talked a single one of them into doing this. And I don't exactly blame them, so we have to figure something else out. And as seems to always be the answer anymore, the thing we figured out was artificial intelligence. So using a program called Deep Lab Cut, we can actually take our hand digitized data, feed that into Deep Lab Cut. Deep Lab Cut creates a neural network, trains a neural network in order to actually recognize, okay, when I see an image looking something like this is the wingtip, this is the nose, this is the elbow, so on and so forth. And then we can go in and feed the neural network all of our videos. And this video is not going to work either, is it? And it will go through, mark every single point in every single frame. Way faster than us humans can do it. Yep. And then once we've marked all of the frames, all of the videos, we can go back and reconstruct, please work. Where's my mouse? Completely reconstruct this bat's flight. And so now, rather than just every frame that we've digitized calculate the kinematic parameters, we can calculate the kinematic parameters for every moment that this video has recorded. So, downside, as I think we all know by this point, in the era of ChatGPT and all the other large language models, artificial intelligence is a little messy, right? I can't just throw stuff in and expect it to be perfect when it comes out. I do need to go back and do some double checking. So this is actually a graph you can imagine if you look straight down, if you look top down on the bat as it's flying, we just straightened out the flight, and this is all of the points as they travel through space. So looking at this flight, this one's actually pretty good. I see a couple of moments where I maybe don't have a lot of data points. The data points themselves are the X's, the line is just an interpolation line. There's maybe a couple points of a little bit messy data, but overall, this is a really nice flight. This is a pretty clean reconstruction. This is what I usually see. So the elephant in the room is right in here, and you can see this red line, the right wingtip is on the left side of the bat. So the bat's flying like this for a moment. I've spent several hours staring at these bats flying. I've never seen one of them do this. So that's nonsense. This is probably an indication that right in here, Deep Lab Cut has never seen something like this. It could be a camera angle that just by some coincidence we've not actually digitized. We've not trained the network to recognize. It could be the bat is flying behind a lamp or something. Not sure from this. But what we do is go back, add in some digitizations in this range, and hopefully it cleans it up. And so this was a fairly iterative process. It's kind of the point. You go back, you go in, you train Deep Lab Cut, see what doesn't work, fix it, and move on. And eventually you get some pretty good stuff. So I do want to pause for a moment and point out this really nice case study that brought us to a pretty large realization, is that we were all very excited when we found this absolutely gorgeous, almost loop-de-loop like curve. This is a top-down view, so it's just a very continuous turn. And looking at this, initially we all said, this is probably just one single turn, right? Maybe I could split it here and be like, that's one sharp turn, this is a less sharp turn. But overall, it seemed like one turn. Thankfully, we did do a little more digging, and we realized that this bat is actually, it feels more like this bat is doing dozens and dozens of turns, like every wing beat is its own turn. It's kind of hard to see the reconstruction from here, but even just looking at the bat flying, you can see, so he's rolling here more, i.e. turning more sideways to make a turn. Let's see. So right around here, he's making that sharp turn, and then he kind of levels out, makes a less sharp turn. There he slows down before speeding up again. That was almost a hover for a second, but in looking at, this is wing extension, just how much is one wing spread out compared to the other. This is turn radius, which I'll define formally in a second, but it's just a measure of how sharp a turn it is. These values are the turn radius is constantly changing, and the wing extension is constantly being modulated to account for that turn. So it was somewhere around here where we just said, you know, we can't do this on an event by event basis, can we? We're going to have to split this up into every single wing beat and analyze every single wing beat separately, because every single wing beat seems to be its own adventure in itself. All right. So enough of how it was done. Let's actually get into what came out of this. Repertoire results. Initially, we had 99 events that I wanted to analyze. Deep Lab Cut really did not like some of them, so I ended up with 75 events that were somewhat usable. And the initial goal was to at least just split these up into turning flight and changing elevation, ascending, descending level. And potentially, there was thought about breaking out a separate reorient category, because they're qualitatively, there are flights where the bat just seems to be flying forward and then suddenly it's facing the other direction. That we were like, this looks like it should be separate. This looks like it's using different mechanisms. It looks like an interesting case study in itself. So before getting into the actual repertoire, I do need to make sure that we are on the same page for some of these units. These are the two most obvious, in a sense, units to try to separate into. Radius of curvature, or the turn radius, is just the radius of the circle of best fit for that part of the flight path. Basically, it's just a measure of how sharp a turn are we looking at. And then angle of ascent is just the angle that the velocity makes with horizontal. So how sharp up or sharp down is the bat flying. So, and these are the most obvious just because radius of curvature seems to be a really nice intuitive way to split out turns, angle of ascent seems to be a nice way to look at the changes in elevation. Anyway, so this is all of the flight events. Y-axis is angle of ascent. I know that's not there, but it's supposed to be angle of ascent. Question is now, can we split this up somewhat satisfactorily into our turns, into our ascents, so on and so forth? Initially, I kind of wanted to try to make this as objective as possible. So the initial approach was a clustering algorithm. Try to use clustering algorithms. See what a repeatable process does to separate these up. And I tried a lot of clustering. None of them really made any sense, produced anything good. I mean, you can see on, let's say this one, almost everything is split up based off of angle of ascent alone. So I have very strong ascents, moderate ascents, level flight, decent, strong descent, stronger descent, I guess, dives. There's no turns in this, is the problem. And so then we thought about doing a more heuristic approach. Can I just draw a line somewhere and say, okay, this is where I'm going to cut off ascents. This is where I'm going to cut off level flight. This is where I cut off descents. But there's a more fundamental problem going on here, is that, let's say that I tried drawing these lines at plus minus 10 degrees. So greater than plus 10 degrees, your ascending flight. Between plus and minus 10 degrees, your level flight. Below 10 degrees, your descending flight. You notice along all of these lines here, there's a bunch of points clustered around that line. And those points clustering around that line are going to make ascending flight look a lot more similar to level flight than maybe it should. And that's going to come along later, muddle analysis, and generally make life miserable. About the only way to avoid that would be like draw this line all the way down here to like negative 50 degrees. But it feels to me like if a bat is flying downward at 30 degrees below horizontal, that should be a descent, right? That shouldn't be level flight. So it was nigh impossible to draw these lines such that they didn't just separate a bunch of very similar points, and they still felt physically sensible. So instead, we just made the decision, it's impossible. We cannot really draw effective lines and create a strong repertoire. It's probably better to just analyze all of these values as continuous. So as the turns grow sharper, what happens? As the bat flies more up or more down, what changes? So kinematic results. What is actually changing? Before we actually get into the results, we do have to do some math. I apologize. This is a nice little formula from steady state aerodynamics. The radius of curvature, there's an R over there. Radius of curvature is equal to the square of velocity divided by acceleration due to gravity, g, and the tangent of the roll angle. I'm not going to go really deep into the geometry of this formula, but I do just want to build up some intuition real quick. We're saying that the radius of curvature is directly proportional to the square of the velocity. So if an aircraft or a bat potentially is flying very fast and it tries to make a turn, that turn is automatically going to be much wider than it would be if it were flying very slowly. And then it is also inversely proportional to the tangent of the roll angle. And this is just saying that when the bat or the airplane is not rolling, it's going to fly roughly straight. When it starts rolling more, it creates a much tighter turn. I think we can all draw some intuition from this with just paper airplanes. If you've not played it with one yourself, you've probably seen other people playing with them. If you manage to throw a paper airplane completely level, it just flies for forever, right? But the moment that it starts turning and it gets really sharp is when it starts that death spiral downward. So, fun thing is, this model actually matches the data surprisingly well, especially for turns like under 2 meter radius of curvature. We have a very strong fit. Whereas when we start getting into wider turns, the fit is not nearly as good. And this may be partially just due to the geometry of the unit. if I have the radius of curvature over the space that a bat would be moving in a single wing beat, radius of curvature of 3, radius of curvature of 4, these both just kind of look like straight lines. Whereas when we get very tight, down towards 0, a turn with a radius of curvature of 0.5 looks very different from a radius of curvature of 0.6.
Can you explain what's on the y-axis?
Oh, yes. Thank you. So the observed radius of curvature is on the y-axis and the theoretical is on the x-axis. So we're just seeing a pretty good one-to-one relationship between those two variables. Where was I? Tight radii of curvature. So as we get into these very wide radii of curvature, could partially be just noise, is making a small bit of noise results in a large change in the rate in the observed radius of curvature. The other way to look at this is rather than, okay, observed versus expected, what are the contributions of the velocity and the roll in real life? Roll angle is on the y-axis, flight speed down here, and we have mean radius of curvature as on a log scale as the colors. And so it's a little bit hard to see without the left side of the graph. But one of the first things I noticed was, okay, looking at this, I see mostly purples over here, which are very wide radii of curvature, very straight flight. And then as we move this way, I start seeing more reds, which are the much tighter radii of curvature. Whereas if we go up and down along the roll, I see a lot of purples, I see a lot of greens, and then way at the top, I see a lot more greens. And these are all kind of middle ground radii of curvature. So that kind of inspires the question, does that mean that flight speed is a little more important than it is radius of flight speed, a little more important than it is the roll angle? And so to answer this, we can imagine, if you think about this as being like a 3D graph, we can rotate this so that the mean radius of curvature is on the y-axis, and then flight speed and roll angle are on the x-axis. What you can kind of see here is flight speed has a much tighter correlation than does roll angle. They're both reasonably good correlations, but the speed is really the tightest correlation. And I have standardized coefficients on here. Standardized coefficient is just saying one standard deviation change in the input produces this many standard deviations changes in the output. It's a measure of effect size. So if ignoring the sign, if I have a large standardized coefficient, it's a large effect size. The effect size for the mean flight speed is 0.39, roughly 0.4. It's cut off. And over here we have 0.25. So this is basically saying mean flight speed seems to have a much stronger effect on the radius of curvature than does the actual roll. Now, we do have the question, okay, how does this roll get produced? And so I see a play sign, so hopefully this will work. So we actually went in and created various case studies in order to try to determine this. So what you're seeing is 3D reconstruction in the top left, the actual video digitized by Deep Lab Cut in the middle. This little guy over here is the roll angle, so how sideways is the bat. And then we have various wing parameters plotted across time so that we can see asymmetries. And of course, my labels are cut off, but I think we can see radius of curvature seems to be dropping right around there. And we can see the roll angle absolutely increases. And that seems to be associated with this asymmetry in the stroke plane angle. Stroke plane angle being the direction that each wing beats. So in this case, looking at this going, okay, I think that I can associate this turn, this production of roll with stroke plane angle. Cool. Let's do another one real quick, as soon as this moves on. All right. Hello? There we go. All right. So here comes the turn right there. Did y'all see anything? I didn't. You could potentially argue this second graph is wing extension. Yes, wing extension. You could potentially argue that this asymmetry in wing extension might be what caused it, but if you pay really close attention to the 3D reconstruction, it kind of glitches out right there. So I think that this apparent asymmetry is just due to the glitch in the reconstruction. Now, those would be frames that we throw out in a more quantitative analysis. So, and especially, I don't really see that wing asymmetry, that wing extension difference when looking at the video. It sure looks to me like what's going on is she just gets her wings above her, manages to get the center of mass ever so slightly off center, and then gravity applies the torque to create that roll. Which, unfortunately, that's not something I can quantify. Not with this method, at least. We really need dynamics modeling to really see if that's the case. So in this case, it would be a little hard to go back and actually associate a standard wing asymmetry with this. And that's kind of a shortcoming of the method. And believe me, I created lots of linear models, mixed effect linear models, trying to assess all of these asymmetries in wing extension, wing supination, stroke plane angle, wing beat frequency. There were no good associations with any of them. And again, it kind of comes back to this idea. The bats have very complicated wings. They have many, many different ways to create these force asymmetries, and this method just can't account for them all. We are missing out on the wing camber. How curved is the wing? We're missing out on the wing compliance. How much is the wing stretching? How much is it stiffened? I can't account for where the center of mass is and if they're using weight manipulation. And in the end, there's just so many variables that could be going into this. The bat could be, you know, all of these, the asymmetry that the bat decides to use could vary based on the individual. It could vary based on ambient weather conditions. Could be due to the desired turn radius. So the scope of this experiment was just a little too broad, potentially, to actually get into how are these rolls initiated. But that said, I do have better news when it comes to ascending flight, descending flight, and the actual flight speed. But before getting into those, I want to make sure that we are all good. We are all on the same page as far as what these kinematic parameters I'm about to talk about actually mean. And my GIF isn't working. Wonderful. Wing beat amplitude, it's the first one, most basic, it's just how big is the bat beating its wings. So top of the wing beat minus the bottom. Just how big is that wing beat? Wing beat frequency, if things work, that bat would actually be flying. But it's, technically speaking, how many wing beats would fit into the space of a second if that bat continued beating its wings at the same rate. In practice, we just measure how long the wing beat takes and then take the reciprocal. That gives us frequency. And finally, stroke plane angle. This is really hard to draw in two dimensions. So watch me instead. If I were a bat and I'm beating my wings, as I move my wings, the wingspan line, which is basically my arm, is tracing out a plane as it goes through space. The angle that that plane makes with horizontal is the stroke plane angle. So it's basically a measure of which direction is the bat beating its wings. 0 degree stroke plane would be it's beating its wings straight forward. 90 degrees straight up and down. 180 would be like the bat is swimming forward. All right, we're good with these because we are now plotting stuff. And the y-axis is actually on there. Yes. Okay, so looking at angle of ascent, we see by far the strongest correlations with wing beat amplitude and flight speed, actually. So likely what's happening is, to a very large degree, the wing beat the bat is trying to fly upwards just by displacing more air, beating its wings bigger and moving more air downward, hence accelerating itself upward. Stroke plane angle, which direction the wings are beating, also plays into that when it's trying to fly up more. It beats its wings more vertically in general. And flight speed. Flight speed is a little interesting because there actually is a steady state aerodynamic equation that predicts the amount of lift something experiences is proportional to the velocity, the square of the velocity, which we're actually seeing a negative relationship here. A little bit backwards compared to the lift equation, but what this is consistent with is the bat is just letting gravity help when it's descending. So as it's going down, gravity starts acting on the bat and is accelerating itself downward, hence increasing the overall speed. Wing beat frequency is another really interesting case because I look at this and I see no correlation whatsoever. Apparently there is a statistically significant correlation there. That said, looking at the standardized coefficients, the coefficient for wing beat frequency is very small compared to all of the others. So it seems like this is a relatively minor factor in whether the bat is flying up or down or level. So moving on to flight speed, there is, as we just established here, there is a bit of a confounding variable if I include angle of ascent, because the bats that are flying downward are automatically flying faster. So if I'm just trying to look at flight speed, automatically I know those descending flights are going to be the fastest, no matter what they're actually doing with their wing kinematics. So instead of analyzing all flights, I just analyzed those flights between 10 degrees above horizontal and 10 degrees below horizontal. These are roughly horizontal flights. And I mean, within a linear model incorporating a linear model with angle of ascent and flight speed within this range really does not see any correlation. So we're filtering from all of the wing beats that we have to just those that are relatively horizontal, between plus and minus 10 degrees. And thankfully, they do have roughly a similar distribution, so I'm not skewing anything here. But what we're seeing is, as I said, angle of ascent and flight speed, no real correlation here. Thank goodness. Our largest effect seems to be the stroke plane. So if they're trying to fly faster, they're beating their wings more vertically, less forward. And there is a correlation with wing beat amplitude. This one's a little weird because it's a negative correlation. So if they're trying to fly faster, they beat their wings smaller, which is inconsistent with a lot of previous literature. This may be partially due to some outliers in the filtered data set, but it is an interesting result. And wing beat frequency down here, not significant. The slope is not significantly different from 0. Basically, wing beat frequency does not seem to have any effect on the flight speed. All right, so what are some of the broad conclusions that we can draw from this study? First thing, the roll and velocity model actually works pretty well for bats flying in a flight arena for at least Coriolanus townsendii. And between the two variables of flight speed and the roll angle, it seems like the flight speed is the more important of the two. If you're trying to make very tight turns, you have to be flying very slowly. And this is actually, we do have another project going on within the Corcoran lab that's not doing this and looking at everything that one bat can do, but rather looking at level turns across various species of bats. And we have some preliminary results from that one suggest that a lot of the bats that fly faster than Coriolanus townsendii cannot make those tight turns like cories do. So potentially, we're just saying that flight speed is the most important factor in being able to make these tight turns, being able to maneuver very carefully, very quickly. For angle of ascent, it really seems to be the wing beat amplitude and the stroke plane angle are the most important factors. And for the flight speed, once again, stroke plane angle seems to be the thing that they adjust the most. What about wing beat frequency? We did see that it had a small effect in the angle of ascent, but visually did not seem to have a correlation, and there definitely was not a correlation with the actual flight speed. So, question is, what is wing beat frequency actually used for? One of my mentors, Dr. Sharon Swartz, has hypothesized actually that the wing beat frequency is driven by a central pattern generator within the bat. So kind of like how when we walk, we're not really thinking about our legs, right? We have other mechanisms doing that for us. And as a result, we kind of have a pace that's most comfortable for us that we just walk at automatically. And if we want to walk faster than that, or if we want to walk slower than that, we have to actually think about our paces, right? It seems to be something similar going on. It's potentially something similar going on with bats, that the wing beats themselves are generated with a central pattern generator. And then maybe they adjust them slightly for flying upwards or downwards, but for the most part, that's just kept constant for the flight because it makes it easier for the bat to focus on the more important things like the wing beat amplitude and stroke plane angle. This may be some early evidence for this idea that the wing beats are driven by a central pattern generator, not actively modulated by the bat. And finally, so what are we actually doing with, what can we actually do with all this knowledge now that we've gained it? First thing is, this is, as far as I know, the first study that's actually taken one bat, looked at all of its flight maneuvers, and done so in a relatively large data set. So it's kind of cool, and we have proven, yes, the methods paper we just published is practical. Second, looking at models, there are lots and lots, maybe lots and lots is a bit of an overstatement. There are several models out there, papers out there that have modeled the movement of air over bats. You know what those bats are doing when they do the modeling? Sitting here like this. Do bats actually fly like that? No. So the hope is that we can, now that we have this positioning data, now that we've figured out some of the kinematics, we can actually take this position data, stick that into the models and see, okay, how do we expect the aerodynamics to change over the space of a wing beat cycle? And going back and looking at some of those more complex turns that we saw, how does weight manipulation play into the bat's flight? Looking more at the physics and how the physics come into play in bat flight like we've seen here. MAVs, micro air vehicles, very fancy name for drones. These there are robot makers out there who have attempted to recreate bat flight with bat-esque drones, and I mean, they work. But they're not nearly as good as an actual bat in real life. And so now understanding a little bit better how the bat accomplishes all these tighter turns, these more complicated maneuvers, we can try to go back, reflect that in the robot design. And finally, going back to Norberg and Rayner, 1987, we can try to verify their or tighten up, correct their predictions of, okay, this bat flies like this, so it must have this ecological niche. And saying, okay, instead of just looking at the aspect ratio and the wing loading, we now know this bat really flies like this. So how does that affect its niche? So hopefully this is the beginning of the beginning of more studies a lot like this to look at several different species of bats and then compare how they can fly, compare that to their ecological niche. And of course, I have to thank my graduate committee for being the graduate committee. Thanking Dr. Jonas Håkansson. That took another 6 months to learn how to pronounce. Jonas Håkansson for introducing Deep Lab Cut into the lab, teaching me how to use MATLAB, all of the tech stuff, and what is steadily growing to be a small army of undergraduates who have contributed to creating the digitizations as training data for Deep Lab Cut. Currently, Katrina Coetting, who has had the thankless task of going through all of the flight events and marking stuff that needs to be taken out. And with that, I will gladly take any questions you may have.